PS2. So Dr. Richardson is an expert on both theory and practice of information theory. He obtained his PhD from MIT in 1990 under the supervision of Professor Mitter, and his bachelor's and MS from University of Toronto in 1986. After graduation in 1990, he spent 10 years in Bell Labs in the Mathematical Research Center. And after that, he joined Flarion Technologies, and he led the system team, which was responsible for coding and modulation of flash OFDM technology, which was the main invention of Flarion. Then Flarion was acquired by Qualcomm in 2006, and since then he has been the VP of Corporate R&D there. Dr. Richardson has made many contributions, many significant contributions to information theory. In particular, if I want to name a few of them, he has a trio of seminal papers which appeared in February of 2001 on LDPC codes. And in particular, one of those is titled Capacity of LDPC Codes under Message Passage, and won the Best IT Paper Award in 2002. And he has authored the famous book on modern coding theory with Rudy Orbanki. And I'm sure many of you have seen the book, own it, have read it. If not, make sure you have it. This is a wonderful book. So with all that, join me and welcome Dr. Richardson as our one lecturer.
Thank you. Thanks, Okay, this is working. So good morning, everybody. So what I'm going to talk today about is some relatively recent results, which allowed us to reach the Shannon limit in point-to-point channels, binary point-to-point channels. Okay, I'll be remiss if I didn't say a few words about the benefactor of this talk, especially because he's in a position to fire me. So I better tell you a little bit about him. So Roberto Padovani, after 2011, was CTO in Qualcomm, which he joined near its founding, and he's since given up that very demanding role, and he's now sort of EVP and fellow. He was a student of Jack Wolf's at the University of Amherst, and from there he went to Linkabit and then to Qualcomm. Okay. Now, actually, I feel a bit like a bit of an imposter here because when I was a grad student, I never took an information theory course, including one like this. So maybe I'll describe a little bit how I got started in the field. So in 1994, I was working on this project which was aimed at doing data storage using holography. So in Bell Labs, they developed new materials and new techniques and also a whole framework. It was advanced enough that it was spun out as a startup in 2000 under the name of Interface Technologies. And I was working essentially on the signal processing side of it. And I had a background in some background in computer vision, so this was essentially 2D signal processing problem. And one of the things they needed was coding solution, error correcting coding solution for the technology. And this was just immediately after the invention of turbo codes. So I started going to talks on turbo codes, trying to understand what was going on. And that's how I got interested in the field. Now, maybe I should mention what happened. So there was a joke that used to go around about holographic data storage, which was that holographic data storage is the storage technology of the future, and it always will be. And, and the company lasted for 10 years, but that joke still seems to be true. Okay, so what I did do instead was in 1999 or 2000, I joined Flarion, and as Ellen mentioned, and one of the things that we did in Flarion was develop this LDPC code technology. So here was I went to the Wayback Machine. I was able to recover Flarion's web page, and there you'll see a product, Vector LDPC. So we developed LDPC as a product, and one of the things I'm actually quite proud of is that we were able to sell that solution, both the hardware design and the software and analysis techniques, into the magnetic storage industry. And a couple of years ago, hard drives started shipping with that technology in it. Here's an example. Okay, so enough about me. Let's talk about Shannon. So Jack Wolf calls this kind of picture the coat of arms of information theory. I'm sure you're all very familiar with it. I only want to make a few comments. So one of the things I think is most important from a practical standpoint is this separation theorem. So Shannon showed essentially that without loss of efficiency, in some sense, you could separate the problem of compression and source coding from channel coding. And I think that the best analogy I can think of the importance of this is the invention of money. So if you think about what you store on your hard drive now or what gets sent over the air in a wireless system, really it's just bits. It doesn't matter anymore whether it's video or audio or a file or something else. It's all just reduced to bit. As Bob Gallagher said, Shannon invented the bit, and I think bit is essentially like a currency. And what it allows us to do is separate the technology problem of handling information sources from storing and transmitting. And this has had a huge, of course, impact on all the technology that we see today. So in some sense, I think this is the most important contribution of Shannon. In this talk, I'm going to focus just on the channel coding problem. Another nice thing about the separation is it allows us to isolate nice problems to work on. And I think the channel coding problem is in some sense the nicest and cleanest. And generally speaking, the problem is always to get information over some physical channel. And the math always just reduces to probability. You have some conditional probability. You transmit something X, and you receive something Y. X is going to be an element of a code. And then, given your observation of Y, you try to decode. So the optimal decoding is just to compute, maximize the posterior probability of the transmitted code word. And although I'm not going to talk about optimal decoding, we're going to talk about some suboptimal decoding techniques. But they all have this flavor in the sense they're trying to compute some kind of posterior probability or approximate it very well. And this sort of approach, using probability to try to do decoding, has sort of dominated the field for about the last 10 years and allowed us to get very close to the Shannon limit. Okay, so to make the talk sort of simple, relatively simple, we're only going to focus on binary codes. So for the technical side of the talk, we're talking about binary strings of length n. And so you can think of the bits as either plus minus 1 or 0, 1, whichever is more convenient. And among these sequences, you choose a code. So code will have 2 to the Rn elements. R is the rate. So basically and mostly we'll focus around rate 1/2, just to be more concrete. But the code rate is just a measure of what fraction of the bits that you're sending can be considered information bits. Furthermore, we're going to focus exclusively on memoryless channels. So memoryless channels means that each bit gets transmitted, it goes to the channel, you make an observation, and they're all independent. So the conditional probability for the observed sequence is just a product of the conditional probabilities for each bit. And we're also going to focus on just symmetric channels, which means essentially here that if we transmit a -1 instead of a 1, essentially all the probabilities just get flipped by the sign. Of course, this depends on what y means, but this basic symmetry is central to what I'm going to be discussing. Okay. So one question is, whether binary is good enough. So in practice, especially, for example, in wireless, binary codes are used nearly exclusively. And the reason is because if you want to go to higher spectral efficiency, then what you do is you map into a constellation, typically quadrature type constellation like this. So you just pick some number of bits, and it gets mapped to a constellation point, and then at the receiver, you project down back onto the bits, compute probabilities, and process them. So binary is not really restrictive, doesn't limit your spectral efficiency in wireless. So another example of why memoryless is good enough is the magnetic recording channel. So when we developed technology for the magnetic channel has memory because of the way that the reading works on the tracks on the disk. This intersymbol interference between the different domains. So the way that was handled is that you represent the memory in this case as a trellis, which is capturing all the structure of the memory channel, and then outside of that you had a binary code, and the two interact, and that's how the system was designed. So even when there's memory in the channel, very often you use a code that was designed for a memoryless channel. Okay, so it's a channel coding problem. So in a sense, Shannon reached capacity in the very beginning. The only issue was that in order to get there, he used random codes, which are completely impractical. So there's a famous quote from Wozencraft and Griffin that at the time, basically, if you pick a code at random, it works very well. Everybody knew that. And so the folk theorem was that almost all codes are good in the sense of probability, except for the ones we know. So as soon as you try to impose structure, it seems that you lose the sort of optimality. So in some way, the conflict for many years has been how do you provide enough sort of complexity in the code and still enough simplicity in the structure in order to get efficient operation. So that's been the challenge for several years. And I guess recently, since the challenge has finally been met. Okay, so here's where we were in 2000, roughly. So around 2000, this is when we published these papers that someone mentioned in the introduction. We were looking at turbo codes and LDPC codes. And here, what you see are just some performance curves for these coding systems over the Gaussian channel. And so the axis in the bottom is measuring just energy, how much energy is put into the signal. And the curves are the performance curves of the codes. Vertical axis is bit error rate. And on the left, you see the channel limit. So everything to the left of that black curve is unreachable. And we can get to the right. So the thing I want to point out are these arrows at the bottom. So these are the so-called thresholds of these systems. So these systems are asymptotically going to achieve the threshold performance, and the thresholds are something we know how to compute. And so the design that this graph is representing was an improvement from the green curve to the red curve that we got by introducing more structure into the design of the code. And the turbo codes were the sort of state of the art at the time, and that was the blue curve there. So I'm going to talk quite a bit about these thresholds and what they mean and how we design them. Okay, and then a little bit later, I had a summer student, Se-Young Chung, who worked very hard to try to set the world record. And so he pushed this technique of trying to optimize the structure of the code far enough on the Gaussian channel to get the threshold at least 0.0045 dB away from capacity. And this is essentially a numerical result. I mean, it's correct in the sense that the numerics computes an actual lower bound, but the point is that we believe that this kind of system could actually achieve capacity, but we still haven't proved it. That's still an open problem. What I'm going to talk about today is how we sort of circumvent that problem to actually get to capacity. But at this point, people believe that we're essentially there. And so over the next few years, people were starting to write the epitaph of coding theory. At the top, you see a comment from Bob McLeese in his 2004 Shannon lecture, and he was speculating in a way far into the future. People look back and what will this period mean? And so he talked about Shannon, how 1948 invented information theory, and within 50 years they're effectively there. In 2007, Dan Costello and David Forney published this paper where they essentially say that we're at capacity, at least we're at the end of the road. We finally produce coding schemes that approach Shannon's limit and so on. But, that's not quite the same. Being at the end of the road isn't quite the same as getting in the house, right? So, quite surprising, just in the last few years, there have been two breakthroughs in a way. Both of them involve some new phenomena, and both have led to codes that actually can provably achieve the Shannon limit. So the first was polar coding. It was first announced by Erdal Erkan in 2007. The main paper appeared in 2009. And just this year, myself and Rudiger Banki and Srinivas Kudikar were able to prove that a form of LDPC codes can also achieve the Shannon limit. And moreover, they can do this in a sense that's universal. So these are two new phenomena, and both the phenomena have been applied to many other settings, so they seem to be both powerful and interesting, and that's essentially what my talk is about today. I'm going to try to convey essentially the main ideas that go into achieving the Shannon limit for these two decoding systems. Now, the first half of the talk probably is going to be just laying the foundation. So I'm going to spend a lot of time talking about binary symmetric channels and symmetry and processing. Like I some functionals on those channels, entropy and the Bhattacharya parameter, and degradation. So these are the main things I need to describe concerning the binary memory symmetric channel. So one thing I want to say at the outset is that, at least from my perspective, a really nice way to think about these systems is to sort of broaden the view of what we mean by a channel. So typically, when people think of a channel, they think of sort of just the physical portion of the system. So for example, in a radio, maybe you think at the antennas, or just beyond the antennas, maybe after sampling or something like that. But when we think about the analysis, we're really just looking at conditional probabilities. And any kind of processing you do, including processing a code, for example, could be thought of as part of the channel. And that turns out to be sometimes a very powerful way to look at the problem. So I can't really unify polarization and spatial coupling without talking about density evolution in LDPC. So density evolution is the main tool that allows you to compute the thresholds I mentioned. And these thresholds and fixed points of density evolution system are the essence to the analysis of these kinds of systems. So I'm going to talk about that. And in the second half, I'll apply those ideas in the polarization and spatial coupling. Okay, so the channels. Okay. So I showed this slide earlier. This is just the class of channels we're going to be talking about, binary memory symmetric channels. So these are the standard examples that you see in all the papers, for example. And so the three examples are the binary erasure channel, the symmetric channel, and the AWGN. So each of these has a symmetry property. You can just see that from the pictures. And the simplest one is the binary erasure channel. Here, essentially what happens is it either gets received successfully or it disappears. And this, the numbers that I put in here all indicate sort of what the channel, what the parameters look like at capacity half. So these are all examples of capacity half channels. Binary symmetric channel, of course, is just flipping out of white Gaussian noise. You think of transmitting either 1 or -1 and adding a Gaussian random variable. Okay. So the main point I want to make now about the symmetry. So if you think of the binary symmetric channel, you can think of it this way. You transmit a bit, and then you're going to observe something. Now, based on the observation, you can make a decision. Was it more likely to have been, say, a 1 or a -1? And associated to that decision is some reliability. For example, the probability of error. So if I think of a transmission from a bit to some estimate of the bit, and some measure of the reliability of that bit, then this essentially characterizes the channel entirely. So the point is that if you want to think about these channels, then in some sense, you always want to reduce it to this. So you have a decision and a reliability. Now it turns out when you want to characterize the channel itself and its quality, all that matters is the distribution of the reliability. So the symmetry essentially takes care of the decision, and all we really need to focus on is what happens to the reliability. Okay, so here's some examples. So if I look at the cumulative distribution of the probability of error for these three channels at rate 1/2, this is what it looks like. So the binary symmetric channel, for example, basically there's only one reliability, which is the probability the bit was flipped, in this case 0.11. A binary erasure channel either have reliability 0, meaning probability of error 0.5, or reliability essentially 1, probability of error 0. And the Gaussian is, like you see here, a little more complicated. Okay, so we know that Shannon established that channels have the capacity C, which is the maximum rate of transmission. So in the binary case, it's achieved when you put a uniform distribution on the transmit bits. That's something fairly straightforward, so we're just going to assume that throughout. In this case, what's interesting is that if you think about these reliabilities, then the channel capacity just turns out to be a linear functional of the distribution of the reliabilities. So in particular, for the binary symmetric channel, it's just, of course, just the entropy function, or 1 minus the entropy function, gives you the capacity. And what I've given here is a plot of the entropy function. It's a function of probability of error. Okay. And for the general case, essentially, if you just average over this entropy function, you get the capacity for the channel. So the important thing is that the capacity is just a linear functional on the distribution. So once you interpret the channel as essentially just a distribution on reliability, capacity is just a linear functional. And here's an example of the calculation. So for the binary erasure channel, there's essentially 2 possible probabilities of error, either a 1/2 or a 0, and they each have some weight. So, okay, I'm missing the brackets around the 1 minus epsilon in front. But anyway, so these are the only terms that appear, and you end up with the binary erasure capacity. The Gaussian capacity is a little more complicated, but it can also be expressed this way. Okay, so linear functionals on these distributions play an essential role in trying to understand the theory. And one of the most important ones is the so-called Bhattacharya parameter, which is originally introduced as a measure of distance between probability distributions. And some notation, so I'm going to use this W quite frequently to represent a channel. There I'm essentially borrowing notation from the polar coding papers. And what it is essentially expected value of the square root of p times 1 minus p. So for the binary symmetric channel, it's simply 2 times this functional of the probability of error. And in the general case, it's simply the average over the distribution of that quantity. Okay, so I'll come back to why it's important in a little bit. Okay. So there are certain representations of these channels which are critical to the analysis. Here's a few. The most common one is the log likelihood ratio. This is what's essentially used in practice. So it's just the log of the likelihood ratio of conditional probabilities of the bit being either 0 or 1, which under the uniform prior is the same as the posterior probabilities. Another important one is the so-called difference metric. Actually, I'm not sure if there is a formal name for it, but if we look at the difference between probability of bit being a 0 and a 1, this difference plays an important role. And I already mentioned the probability of error. So the important thing is that I can use any of these quantities to represent the channel. So if I look at the distribution of them conditioned, say, on transmitting a 0, and for a binary symmetric channel, this completely characterizes the channel. And if I look at the distributions, then capacity, Bhattacharya parameter, and many other functionals of interest are just linear functionals on those distributions. In fact, because of symmetry, it's enough just to look at the distribution of the absolute value. All the information is in that. Okay, so here's an example. So in the case of the Gaussian channel, the nicest form is a log likelihood ratio. So if you transmit it plus or minus 1 and you add Gaussian noise, then the log likelihood ratio is simply a scalar multiple of what you receive. And the multiple is just a function of the SNR, essentially. And so if you assume that a 0 is transmitted, now you look at the distribution of this y, it's a Gaussian distribution. What's interesting about it, and this comes out of the symmetry, is that the variance and the mean are tied together. So it's really only a 1-parameter family of Gaussians. And as it says here, the mean and the variance are tied together. So symmetry kind of reduces to a 1-parameter family instead of Gaussian channels, and they can be represented by these Gaussian distributions. So here's some examples. So red, green, blue is sort of improving channel quality. These are then the distributions of the log likelihood ratio, conditioned on transmitting, say, a plus 1. So if you transmit a plus 1, you're more likely to receive a positive number than a negative number, and these are just the distributions. So underneath we see the corresponding distributions for the binary symmetric channel, and here these are just delta functions. So at the log likelihood ratio of the probability of error of the channel. Okay, so a few more comments. So densities that are important to us, delta infinity for these log likelihood ratios. So basically, if all the probabilities at infinity, that means that you essentially decoded perfectly. So a distribution delta infinity means that delta function at infinity corresponds to perfect decoding. Delta 0 corresponds to all the probability being at 0, which means complete erasure. So these are sort of the extreme densities that we're interested in. So I mentioned that you can actually just look at the absolute values. Another way to see that is if you multiply by e to the minus half x times the density, then this is what you'll see for the Gaussian case. The functions become even around 0. So this is just indicating that, that what's on the sort of negative half axis is actually completely determined by what's on the positive half axis. And the whole distribution could be represented by the absolute value. Now this particular sort of symmetrizing form is actually particularly nice if you want to actually implement density evolution. The other thing I want to point out is that when I'm multiplying by e to the minus half x, then essentially what I'm doing is shifting over. If you think of the Fourier transform, I'm just shifting over by half, which will come back in a second. Okay, so if you look at these Gaussian densities, the log likelihood ratio, the error probability, that is just probability being less than 0. And the Bhattacharya constant is just the integral of this shifted density where I multiply by e to the minus half x. So the Bhattacharya parameter actually corresponds to the evaluation of the Fourier transform of the L density at center of symmetry. So if I take the Fourier transform of an L density, then it has a lot of symmetry, and the center of that symmetry occurs at the point with a real part 1/2 and imaginary part 0. And the evaluation of the Fourier transform at that point is the Bhattacharya parameter. So it's just the area under this even curve. And it has a property which you can see from the graph, or it actually comes out of Chebyshev's inequality, that the Bhattacharya parameter is twice the error rate. And this is important inequality, and the Bhattacharya parameter has been used for years, for example, in union bounds, in bounding probability of error of codes. And it gets used the same way in the analysis of polar coding and in iterative and LDPC coding. Okay, so now I segue into code structure. Okay, so as I mentioned from the beginning, people have been trying to look for codes that were tractable that can still get close to the Shannon limit. So maybe the first step was taken by Elias in 1955, who started looking at linear codes. So he showed that for random linear codes, the capacity could be achieved in the binary erasure channel. And this was generalized in 1961 by Dobrushin to all binary memoryless symmetric channels. And so here's some examples of representations of linear codes. These are actually Hamming codes, not random codes. But nevertheless, the two representations which are important are the parity check equation and the generator equation. So the parity check equation just represents the code as a null space of some matrix H, which is the parity check matrix. And the generator equation gives you a basis for the code, and take your input bits U, multiplied by the basis, that's your code. So the two representations are, of course, related in that the generator matrix spans, of course, the null space of the parity check matrix. So pretty much since then, people have focused almost entirely on linear codes. It was a huge reduction in complexity from random codes, but still not tractable. Okay, so I want to make a quick remark on symmetry and linear coding and a posterior probability processing. So I mentioned earlier that one of the ways to think about these systems is to expand the notion of channel. And this is probably the most fundamental underlying expansion you can think of, and so I just want to quickly describe it. So normally we think of transmitting a bit through a channel, making an observation associated to the channel, but you can expand that notion. So suppose I want to transmit a bit, and I can take that as, let's say, the first bit defining a code word. Maybe it's generator matrix form. So I pick a bit, pick the rest of the bits, so I'm going to generate the code word at random, generate the code word, transmit it. Now at the receiver side, I make an observation for each transmitted bit in, say, the x vector. I make an observation y for each bit. And now I'm going to process back and try to compute what that bit was that I chose. And for example, I try to compute the log likelihood ratio. And the bottom line is that this whole process, assuming that each bit went through a symmetric channel, is that the entire process is symmetric. So even though I've done all this processing of probabilities and I've expanded to a code and so on, if it's linear, then the net effect is still just a binary memoryless symmetric channel, which means the whole thing can be represented by the distribution, for example, of the log likelihood ratio. And as it turns out, for example, in LDPC processing, essentially what's going on is you're doing exactly this process and computing what these distributions look like, and that's so-called density evolution. And it's modeling the actual decoding process. Okay, so also due to Elias in the same year, 1955, convolutional codes. So convolutional codes, so I gave this picture supposed to represent a simple example. So you can think of maybe the U's as representing input bits and the X's as the code word bits. And the idea is that they have to satisfy some parity check relation, which you then make translation invariant, so you just slide them along. So in this case, I've shown two sequences, one on the top, one on the bottom. And the red box represents a parity check constraint, meaning that the sum of all the things it's connected to should be 0 mod 2. So basically it says that all the bits that it's connected to should have an even number of ones in them. And in this particular case, we would think maybe of the U's not being transmitted and the X's are being transmitted. And I chose this example for a particular reason, which I'll come to in a second. But I just want to say that another way to think about the convolutional codes is that the parity check matrix will have this sort of block diagonal structure. So it's not like it's a sort of slanted diagonal, and the slope of the diagonal represents in some sense the rate, but it has this kind of reduced complexity. And that turns out to be very useful in decoding these codes. Okay, so this is supposed to represent very roughly so-called trellis representation of the convolutional code. And so the circles in the middle represent the U's, and the blue circles on the top and the bottom represent the X's, and the red squares represent all the shifted parity checks. Okay. And the green lines indicate which bits participate in which parity check. Okay. Now, because of the sort of local structure, any given output bit, like the one in the middle here, it only depends on some subset of these bits in the middle. In this case, we have 3. And typically what people think of when in convolutional codes is you divide it into sort of the state, which is the memory part of it, the 2 bits on the left, and the incoming bit, which is the one on the right. And the entire structure in the code can be represented in the so-called trellis. So if you pick a set of bits in the middle there, then you can represent it as a path through the structure on the bottom. So if you follow these purple lines, what's happening is each time you transition from one state to the next, you have 2 choices going out depending on a 0 or a 1. You can think of, for example, the gray circles as 0s and the light blue ones as 1s. And essentially what's going on is then the code words correspond now with paths through the trellis. So this picture is called a trellis. And all the information, all the dependencies between the bits, the U's, and the bits in the top are represented in this trellis structure. Okay, so I mentioned the Viterbi algorithm, 1967. This is sort of the bread and butter mainstay for wireless communications for many years. It's essentially using dynamic programming to decode this. So the basic idea is for each state, you compute the best path, the most likely path coming into it, and then you propagate that calculation from left to right. Once you get to the end, you can trace back the solution for the most likely path. And more relevant to what we're going to be talking about later is the Bisset-Giari algorithm, which was invented in 1974. And the difference is that in this algorithm, instead of computing the most likely path, you're going to compute the probability of each path. And then from that, you can compute the posterior probability for each bit. So the idea is that you effectively compute for the entire structure what's the probability that each bit was, say, a 0 or a 1. Now, as I mentioned earlier, you can then view this as somehow enhancing the underlying channel. So if you transmit each of these bits through a channel, and then you do this decoding, you can think of the net effect is having transmitted the bit through some other channel, and it turns out to be better because it's exploiting the redundancy. So apparently there's a quote through to Shannon that codes are in effect SNR amplifiers, and this inspired Baru in 1993 to invent turbo codes. So the idea of just the encoding structure of turbo codes is shown here. You essentially have two convolutional codes connected by a random permutation. And if you think about it from the graphical perspective, it looks something like this. So you have a convolutional code in the top, a convolutional code in the bottom, and some set of bits, in this case the input bits, are copied in one case and the other through this random permutation. And the decoding technique was to essentially apply the CGR algorithm on each code one after the other and exchange information back and forth. And these codes kind of stunned the coding world because they performed quite close to the Shannon limit, and they kicked off essentially a revolution in coding in 1993, which is about the time I got interested in the field. Okay, so subsequent to that, people, in particular David McKay and Radford Neal, sort of rediscovered LDPC coding, which actually had been invented much earlier in 1961 by Robert Gallagher. And I've been using already tangograph representation, meaning these red boxes indicate parity checks and blue circles indicate nodes. And this is now the sort of standard way that people look at LDPC codes, even though the LDPC really refers to the parity check matrix representation. We think of them in this graphical way. So we have a set of bits, these blue circles, and they're related to each other by some set of linear constraints, which are indicated by these red squares, and the green edges only indicate which bits participate in what parity check. So this was, and a lot of the analysis was worked out for these codes by Gallagher in his thesis in 1961. And recently there's been some rapid development and improvement. I guess 1961, the technology really wasn't there to support this kind of coding technique. So its full power wasn't realized until many years later. Okay, now the key point, of course, is not the graphical representation, it's the decoding technique. And Gallagher just called this probabilistic decoding. And what it is messages being exchanged on the edges of the graph, like you see here. And each message simply represents some estimate of the bit associated to the edge. So essentially what's happening is it's a recursive procedure to calculate a probability or some estimate of a probability for decoding the bit. And the messages have structural dependence, and this was the key to Gallagher's insight, that the probability for a bit could be computed recursively. So in particular, if I want to think about one of those messages going out from one of the bit nodes, and I want to trace back how it's determined by messages coming in along the other edges in the previous iteration, and that structure recurses. So Gallagher's insight, and this is in the background you see a picture from his thesis, was the understanding that if you wanted to compute the posterior probability for the bit at the root of this tree, that you could do it recursively. So you start at the bottom, you compute posterior probabilities, and then just propagate it up the tree, and at the root, then you can get the posterior probability for the bit for this tree structure and decode it that way. And that was the essential insight into the invention of LDPC, this recursive computation. Now, it turns out turbo codes can be understood essentially as an LDPC-like decoding. So the main point I want to make here is that the dependency along the trellis of bits far away from a given point decay. So you can actually think of, even though when you decode the trellis structure, it's a global algorithm, it actually only operates locally. And in particular, we know this, for example, what happens in one point in the trellis becomes independent, but what happens at another point in the trellis if the distance is if they're far enough away from each other. And because of that, decoding of the trellis is essentially a local structure. So even though the trellis is completely connected, in fact, what happens is that it sort of breaks up into local structures, and you can still get this kind of tree-like structure to represent a turbo code. Okay, so the analysis that it works for LDPC also works for turbo codes. Okay, so one more development So earlier in 1999, Strom and Zagangos kicked off this area of combining convolutional coding and LDPC in a different way, so not turbo codes. But the idea was to take convolutional-like structure and instead of just having sort of local constraints, spread them out. So these H's here represent big matrices, roughly, say, 2 by aspect ratio of 1 by 2. So each H here, H sub I, think of maybe 2 rows, 2 ones per column, and say 1 1 per, or two 1s per row and 1 1 per column. So that this matrix has, let's say, 6 ones in each row and 3 ones in each column. And so this is essentially an LDPC structure, actually pretty much similar to one of Gallagher's original structures, having 3 bits in each column and 6 in each row. And what they started claiming was that the performance of this type of convolutional code, LDPC, was actually much better than the underlying LDPC. And for a long time, I didn't believe it, and I'll explain briefly why. So I mentioned in the turbo code case, what we know for the trellis is that dependence decays with distance. So here in the middle of this picture, you have essentially an LDPC type structure. And if you really believe in this decay of dependence, then locally that structure should behave pretty much like an LDPC code. And whatever is happening on the boundaries doesn't matter. And that will be true if you extend this long enough. And I couldn't see any reason then why constraining yourself to sort of diagonal structure is going to improve things over, say, having all the ones and zeros just spread out and having a big block. So I was somewhat skeptical about the claims for LDPC convolutional codes. And this development is what led to spatial coupling. And in some sense, I was right, but I was also wrong about the structure of the relationship I just described. And it turns out that these do perform better in some sense. And if you do it right, then you can actually achieve the Shannon limit with something like this. Okay, so that will be later in the talk. Okay, so how do we analyze these systems? Okay, so what's happening in this message passing decoder? So if I think of it iteration by iteration, is something like this. So at the very beginning, I might just take the observation that I got for a given bit and decode it, and I'll get some value. And so without iterating at all, I could just do that. I'll get some performance. Now, if I go one iteration of the decoder, then essentially what it's doing is trying to optimally decode that bit in the center given this picture. So the idea is that this bit in the center belongs to this code, which has this structure looking one neighborhood deep into the graph. And the algorithm is trying to decode optimally that node in the center. If I go to another iteration, it'll look like this. And if you continue iterating, it just gets bigger and bigger, and so on. Now, it's clear that the actual underlying graph is not a tree in the sense that some of these nodes are the same. So depending on how large the code is, at some point you'll be forced to have repetition in the structure. But the basic idea of the belief propagation decoding is it ignores all that and assumes that this is the world you're living in. So the bit in the center acts as if it's living in this infinite tree. There's no repetitions. And the algorithm, iteration by iteration, is expanding that neighborhood and essentially doing optimal decoding for the bit in the middle, computing the posterior probability. So that's the idea of belief propagation. And it's suboptimal for an actual code only because the underlying code structure is not this tree, but actually has repetition. So how does it work? It's really quite simple. Basically, what you do is you send messages back and forth on the edges the way I described, and you update the messages as they pass through the nodes. And the nodes essentially assert the relationships that it represents for the given edges. So, for example, for the variable node at the top, it essentially says that all the bits associated to edges it's connected to are the same bit, and so it asserts an equality relation. At the check node, it's asserting a parity check relation. So essentially, the probability you get the messages that are coming in are just probability distributions on the bits you assert the relation and compute the probability for the outgoing message. Now, the way we analyze this is to think about the messages is essentially representing probability distributions on the bits. We think of them as channels. So each one can be thought of as a binary memoryless symmetric channel. And then what we're interested in is how does that channel evolve? So at each stage, you'll have some distribution on these messages representing the distribution, for example, of the reliability of the decisions associated with the messages on those bits. And those distributions change as you pass through the nodes. And if we can track that change, we can track what's happening in the decoder, at least under the assumption that things are tree-like. And that's density evolution. Okay, so here's one particular form of the calculation. So under belief propagation, the log likelihood ratios turns out just add. So this is just following the laws of probability. So this is, as I mentioned earlier, log likelihood ratios are typically what's used in actual implementations of the decoders. And so for variable node, the outgoing message is just going to be the sum of the incoming messages when those messages are log likelihood ratios. So if we have now the distributions of these log likelihood ratios, exploiting the symmetry, so these are these L densities I mentioned earlier, it means then that the density of the outgoing message is just a convolution of the density of the incoming messages. So density evolution in this case is very simple. It's simply convolution of these L densities. Okay. Now the check node, turns out there's also a convolution operation, but it's under a different representation. I don't want to go into details. But essentially, it turns out these difference metrics just multiply through at the check nodes. And if you take a logarithm, then it becomes a sum. And if you have a sum, then the operation on the densities becomes just a convolution. So we know so again, maybe I should go back. So the idea here, of course, if you think of the outgoing log likelihood ratio, the incoming ones are random variables, and you want the distribution of the sum, then of course it's just given by the convolution of the distributions of the terms in the sum. And the same thing will happen here after we take a logarithm. Just the math is a little more complicated. It's convolution over this underlying space and not over the real line. But structurally it's the same. It's just a convolution. Okay, so I want to give a couple of quick examples which are important for the polar code setting. Okay. So I want to think of a channel like this. So suppose you want to transmit a bit x. So what you do is just repeat it twice, x1 and x2, and you send x1 over some channel w1 and x2 over some channel w2. And you observe y1 and y2. So the channel is x goes to y1 and y2. And it's a binary memoryless symmetric channel. What's its density? And so the point is that, this comes out density evolution. If I have the density for this channel W1, I have a density for channel W2, then the density for this resulting channel is just the convolution of those two densities in the sense of these L densities. So if I wanted to decode, for example, if I observe Y1 and Y2, I could just use belief propagation and propagate it back through the equality node to get the posterior probability of X. And so if I'm thinking about the distributions of those decision processes, then what it amounts to is that the equivalent channel for the bit X is just this convolution of W1 and W2. Similarly, if I have a check node, I can think of wanting to transmit a bit X, and I think of generating X1 and X2 at random so that this parity check is satisfied, which means essentially that X1 and X2 are equal if X is 0 and they're different if X is a 1, and transmit them through. Then the net result is equivalent to a binary memoryless symmetric channel whose representation is essentially this kind of convolution of the two channels. Okay, so one last sort of comment on the Bhattacharya parameter. So if I look at the effect on the Bhattacharya parameter of these two operations, it looks something like this. So the simplest one is the first one. So if I go through this convolution at the variable node side, and the Bhattacharya parameters just multiply. And the reason that happens is because As I mentioned, the Bhattacharya parameter is essentially the evaluation of the Fourier transform at a point of the underlying L densities. And L densities are just convolving on the real line, so the Fourier transforms just multiply. Now there's another relation, of course, that happens at the check nodes. I've written it down here as an inequality. So for the binary erasure channel, this inequality becomes an equality, but for all other cases, there's a slight gap. If you replace the Bhattacharya parameter by twice the probability of error, then this becomes an equality in general. But these inequalities are going to be critical in the analysis of polar coding. So I wanted to point them out while I have the opportunity. So the point is that as when I evolve the channels through these equivalent operations, I can get some idea of the relationship between the underlying parameters of the net channel in terms of the component parts. And the Bhattacharya parameter turns out to be a critical one, and these are the two inequalities with relations which turn out to be critical. Okay, so I'm going to give you an example, a visualization of the density evolution. So here I'm going to do the binary symmetric channel. On the right here I have the representation of the tree structure. I couldn't expand it to full size because it would be far too big. But the idea is you can just think of it level by level as we go up the tree, say towards the center of that circular picture I showed you earlier. And we're just tracking then what's the distribution of the messages going up. So using the L density representation, we imagine we start with the binary symmetric channel. It has a distribution like this, essentially delta function, two delta functions. And this is, again, the distribution conditioned on actually transmitting a zero. So L density. So if we go through one step, and then in the first step, it's still a binary symmetric channel because each node here has the same number of edges coming into it. Then the variable nodes starts to look like this. This is then check node convolution, variable node convolution, check node convolution, variable node convolution, and so on. So this process just continues. And this is an animation of the whole thing. Okay. So the two densities evolving. And what I'm doing in each pass is I'm changing the channel a little bit, making it slightly worse. And what you should observe is that the whole thing kind of slows down and eventually pretty much gets stuck. Okay, actually it's not stuck yet, but if I let it go long enough, it'll move it. Okay, so I want to try to understand this getting stuck process and how then we use the density evolution to do design. Now the simplest case is the binary erasure case. Now the binary erasure case, we can actually represent it very easily graphically. So in the binary erasure case, density evolution looks very simple. You have some probability of erasure coming in and some probability of erasure going out, and the map can be represented just as a function. So here at the top, I have representation for a variable node, in this case degree 3, with some particular erasure probability on the channel. So this blue curve, it's just the input-output relationship of erasure probability according to density evolution. And the bottom one is the same thing for the check node. Okay, so the way that density evolution for the binary erasure channel can be thought of is you take these two exit functions and you sort of swap one of them, in this case the check node function. So I'm going to plot the inverse actually, or if you like to think of it, I'm going to plot it where the arguments on the vertical axis and the output on the horizontal axis, and then we put the two together like this, and then the iteration process can be thought of as essentially evaluating one function and then the next. So the idea is that iteration corresponds to alternating between sort of evaluating the red function and the blue function, so check node and variable node, and evaluation of the check node is horizontal, and evaluation of the variable node is vertical. And so if you look at density evolution, you get a process like this. So in this case, you can see what happens is that it iterates, you go all the way down to 0. And on the right, what I've shown is sort of corresponding effect of this kind of operation for the AWGen and the BSC. Of course, these cases do not have this nice one-dimensional picture, but in a corresponding way, you can track what happens to the distributions as you go from one step to the next. Okay, so in this case, this represents successful decoding asymptotically. So the idea is that if we iterate, then the process is going to go to 0, 0, which means zero erasure, so it's perfect decoding. Now, if I make the channel worse, then the variable node curve kind of moves up like this. And now if I do the same thing and I iterate, I'm going to get stuck. Okay, so then I've blown up this little portion where the curves cross, and the iteration process then is just going to get stuck at the point where the curves cross. And for corresponding parameters for the AWGN and BSC, you can see what happens to the densities of the reliabilities under density evolution, and they converge to some fixed point. Okay, so the basic picture is like this. So for the binary erasure channel, you have these three kind of regimes depending on what parameter you pick for the channel. You're either going to have that these two curves don't cross, in which case you're below the threshold. At the point where they touch, that's the threshold. So at that point, you've failed to go to the 0, 0 point, which is perfect decoding. And if you're above that, you're above the threshold and you get stuck in some fixed point. And this general picture is true even for arbitrary channels. It just doesn't have the same picture. Okay, so here's a little preview of what's coming ahead in spatial coupling. So it turns out in spatial coupling, a new threshold is introduced, and it occurs at some special point like this. So here the idea is if you see this yellow area and the green area, we're going to define something called an area threshold, which will happen when these two things balance. And this turns out to be another type of threshold, which is relevant to spatial coupling and gives an improvement in performance of the whole system, and actually allows us to get to the Shannon limit eventually. Oops, sorry. Okay, so here's what I want to say about this. So LDPC thresholds are characterized by these fixed points of density evolution. So it's very clear in the binary erasure case, maybe less clear in the general case, but I'm going to argue in a minute why they're essentially the same. Okay, so as the infinitely spatially coupled system, which we're going to talk about later, exhibits the same fixed points as the underlying system, but in addition, you get these new fixed points which are going to come up, and they occur only at this critical parameter value, which corresponds to this area threshold I just showed you. So that's something that's coming up later. Okay, so how do we think about the fixed points in the general case? So the main difficulty is that, in these probability distributions, you're dealing with an infinite dimensional space as opposed to just a real parameter. So you don't have the ordering that you have in the binary erasure case that allows you to conclude convergence to the fixed points where the curves cross. So the way we deal with this in general is to use a partial ordering. So there's a partial ordering on the space of channels that makes sense, and this ordering is so-called physical degradation. And the idea is very simple. So you can say that one channel is worse than another, and so if you can sort of represent that channel as a concatenation of your better channel and something else. So if you take the output of a channel and do anything with it, you can only remove information, such as the data processing inequality. So we say that a channel is physically degraded if it has this relationship. So channel A is physically upgraded with respect to B, or B is degraded with respect to A, if this kind of structure holds. So there's something you could do to the output of B to get A involving C. And analytically, I just want to say there's a very nice characterization of this property in terms of these distributions of the reliabilities. So it turns out that physical degradation corresponds with monotonicity of the integral of the cumulative distribution of the probability of error. So the details aren't so important. The point I want to make is that if you represent the channels in an appropriate way, then this physical degradation can be equated to just pointwise ordering, so one function being strictly above another. And the point about this is that since we essentially get reduced to a point-wise ordering of valuation of some functionals, things like monotonicity under degradation imply convergence. So for example, so a sequence of degraded channels is ordered in the sense that the some representation of the functionals, the densities, are point-wise ordered and therefore have limits and always converge. So this implies certain compactness in the space of distributions under the partial ordering. I want to show how you can use that to very easily conclude that the fixed point characterization of density evolution. So, and I want to use this idea of expanding the notion of a channel. So here, so this T represents sort of one iteration of density evolution. So the idea is I'm going to think of a tree, and the bits in the root of, or the leaves of the tree will go through a channel with distribution Q, and the ones internally with the distribution R. So if I do 0 iterations, essentially I'll just get the channel Q. If I think of one iteration, so the leaves go through some channel with distribution Q, and the roots through some channel distribution R. And if I apply density evolution, I'll get the representation of the net channel for the root bit, and I just represent then that by T, T1 R of Q. Okay, so this will be, for example, 2 iterations. So again, we can think of the whole thing as a channel just for transmitting the root bit. So if I imagine I want to transmit the root bit, so I pick a code word from this tree at random, transmit all the bits through the corresponding channels. At the receiver, just compute the posterior probability of the root using density evolution, using belief propagation. Then density evolution, I can use density evolution then to compute what the effective channel is for that root bit. And that's the operator. So the T sub 2 represents that operation of the computing the net channel. And now I could take this transmission and degrade it. And the way I can degrade it is, say, by just removing the bottom level. So it's clearly a degradation. I'm just throwing away information. So I remove the bottom level. And that, since it's a degradation, it tells me that this particular channel is degraded with respect to the earlier one. So as a consequence, just from this sort of high-level analysis, you can see that I get this relationship. So if I do K plus 1 levels with Q in the leaves and R internally, then that's going to be physically upgraded with respect to doing K levels with the distribution R on all the levels. Okay, so now if we in particular put Q equals R, then we just get monotonicity under density evolution. So it means that in each iteration, the net effective channel is getting better and better in some sense, in the sense of physical degradation, which means the thing has to converge. So what this tells you very simply is that density evolution, when you're looking at the density evolution of a decoding process, always converges. Furthermore, if Q is a fixed point of the underlying density evolution, then on the left side above here, I'll just get Q, meaning that in each step, the density Q is a fixed point. Then it tells me that any density I'm going to achieve, or the net effective channel that I'm going to achieve, will always be degraded with respect to Q. So if there's a fixed point in the system, it means then that the density evolution will never get any better than that fixed point. And so the basic picture now that I showed you for the BEC of the crossing curves emerges again for the general case. And so the basic analysis goes something like this. If you think of a family of channels, for example, the AWGN ordered by, say, S and R, then at some threshold value, sigma star, you get a sharp transition between the behavior of the iterative decoding system. So either you're below that threshold, or the channel is better, in which case it'll converge to the Stelton infinity solution, or you're above it, in which case it'll converge to some fixed point. And this threshold value corresponds exactly to the emergence of a fixed point of the underlying density evolution. So in the BEC case, this means exactly the curves touch, and in the general case, it means some fixed point emerges. Okay, so basically one is below the threshold if and only if there's no fixed point. Okay, so the point here, what I want to emphasize is this, that the idea is that characterization of the performance of the system in terms of fixed points is fundamental. So if you can understand what are the fixed points of the underlying dynamical system, you know everything you need to know about the performance. Okay, so density evolution, then once we understand it, basically can be used to model the decoding process. And essentially what we know is that if we want to improve performance, we should try to change the structure in order to get better performance. We should change the structure to try to move the fixed points more towards the Shannon limit. And in 1998, the first step was to introduce sort of called irregular. So Gallagher's codes were so-called regular, meaning that the number of edges coming out of each node type were the same. So for example, 3 edges for the variable node, 6 for a check. And the performance I showed you at the very beginning, so the big improvement over the regular codes and turbo codes was achieved this way just by allowing different nodes to have different numbers of edges. And there are many variations on the theme. Say by 2001, for example, in Flareon, I was using much more sophisticated structures where now to describe it you need a vector of densities, not just a single density, but basic principles are all the same. So just by putting sort of more large-scale macroscopic structure and introducing constraints in the way things are connected, you can get better performance. And in around 2001, for the best structures that I found looked something like this. Details don't really matter. The point is that this basic tool was density evolution and trying to find structures that optimize the performance. So we completely missed spatial coupling, which is just yet another structure. And it also behaves in a very different way than any of these, but it's still in the same spirit. Okay, so here's a quick preview of what's coming up. So, so spatial coupling can be interpreted as just another one of these types of constructions. So the idea here is essentially you have a one-dimensional structure. So essentially the idea is we're interconnecting sort of local LDPC codes with their neighbors. And you get a sort of parity check structure like this, which looks very much like what I showed you earlier for the low-density parity check convolutional codes. And essentially you have this diagonal type structure constraint on the parity check matrix. And for reasons that we'll get into, this type of structure can allow you to achieve the Shannon limit. Okay, so let's see, it's a little early. Okay, so I was thinking I would get to this, start this in the second half. Maybe I'll just get started a little bit in the polarization. So up to now, I've been telling you all the boring stuff, which you need to know to lay the foundation of what we really want to look at, which is polarization, coding, and spatial coupling. And the reason I had to lay the foundation was because I want to use these ideas to describe polarization, coding, and spatial coupling. So just to get started, let's try a little game. Okay, so here's an experiment. Let's just do an experiment. Okay, so pick some number between 0 and 1. Time 1, 2, 3, 4, so on, flip a coin. And if you get a heads, then just take your number and square it. If you get a tail, then take 1 minus your number and square that, and then resolve your number. So basically you're going to square either the number itself or 1 minus the number itself. This gives you a sequence, epsilon 1, epsilon 2, and so on. So, and how does it behave? Okay, so here's an experiment. I just ran this. So I'm starting at 0.5, and the red crosses represent the resulting number. So the first step, basically I'm squaring 1 minus epsilon, and then epsilon, so on. So you can see what happened. It essentially converged to 1. Now if I repeat the experiment, this is the second trace, third trace. After 10 traces, it looks something like this. So basically I had 6 of them going to 1 and 4 going to 0. And after 100 traces, it looks something like this, with roughly 55 and 45 here. Okay. So what if I start with a different initial condition, let's say 0.2. So here was the first trace, second, okay, both went to 0. Third, this is after 10, 2 went to the top, and after 100. Okay, so what's interesting about this? So a couple of things are, first of all, I'm getting some kind of convergence either to 1 or to 0, and the balance seems to be roughly equal to the initial condition. So in this case, if I take the expected value, for example, I have 76 at 0 and 24 at 1, I'm going to get roughly 0.24. And in the other case, it was like 0.45. So what it turns out is that you can show that what's going to happen here is that essentially you're going to get convergence to the 1 and the 0, and that the proportions will be exactly equal to the initial condition. So in particular, if I rewrite the stepwise operations this way, so on a heads, I'm going to take epsilon right as epsilon minus epsilon squared, and on tails, it's just going to be adding the same thing. So you can see basically the number either goes up or down by a certain amount, and the amount is the same whether I go up or down. And that means that the sequence forms a martingale. So the expected value at the next step is equal to what a given condition on the current value is equal to the current value. And of course that can iterate, so I know that as the thing evolves, that the expected value that I'm seeing is not changing. And if it's going to converge then to 1 and 0, the distribution must be the one that gives me the right expected value. Okay, so the process is martingale. So now you just pull a theorem out of probability theory. Bounded martingales converge almost surely, which means that the values of these epsilons are converging almost surely. So that the difference between one step and the next is going to 0 almost surely. And from that, since the difference is just this epsilon t minus epsilon t squared, and it must be going to 0, I can conclude then that converging either to 0 or to 1. Okay, so this is an illustration of the polarization process, and so the process is interesting that it's always going to go either to 0 or 1, and since it's a martingale, there's an invariant, which is the expected value, and that allows you then to conclude that the probability of going to a 0 or a 1 is determined by the initial condition in this simple way. Okay, so just quickly, you can generalize this idea to binary memberless symmetric channels. So start with any channel. Okay, actually, I shouldn't say it in 0, 1, but the channel, a binary symmetric channel, and flip a coin. And this time on heads, we're going to convert the channel by doing this sort of variable node type convolution. And if we get a tails, we're going to do this sort of check node type convolution. So this will give us a sequence of channels. And the example I just showed you was exactly this for the binary erasure channel. So for the binary erasure channel, these are the update operations corresponding to the sort of variable node convolution and check node convolution. And the general result is then that, which I don't get into the details, is that these channels as they evolve are going to converge either to delta infinity or delta 0, so either to perfect decoding or complete erasure. And the probabilities of this convergence correspond to the information rate or the entropy of the channel. So essentially what's going to happen is what's going to be preserved is sort of the information rate of the channel is preserved, and with probability equal to the information rate, it goes to a perfect decoding, and with complementary probability, it goes to complete erasure. So this is the notion of polarization. Okay, so how do we get the invariant? This is a simple, relatively simple information theoretic result, which just shows that the total information rate in the channel, or in this case I'm going to say the entropy, is preserved. And it's actually fairly easy to show, and so the proof is the bottom few lines here. And what I want to prove is the equality on the top, which just says that if I think about these two channels, the two convolutions, and I look at the information rate or the entropy, that's equal to the sum of the original two entropies. And the proof is here on the bottom. So the entropy of the channel is just the conditional entropy of the transmitted bit given the observation. And if we just go through the proof, so I want to think of this situation here indicated by the check node. So we have unknown hidden variable z and variables x1 and x2, and they're all related by this parity check equation. And x1 is going to go through channel W1, x2 through channel W2. And so the net result is I can think about the conditional entropy of x1 and x2 given y1 and y2, and because they're just independent channels, I just get the sum of the entropies. If I knew x1 and x2, then of course I knew z. So the entropy in x1 and x2 is the same as the entropy of x1 and x2 and z. And now I can just use the chain rule of information theory. So if I first look at the entropy of z, and then I condition on z, I know that the sum of these two entropies is the same as the previous line. This is the chain rule in information theory. And on the right here, essentially I'm looking at So now if you think of transmitting sequence this way, so you take a bunch of bits U, you multiply it by some random matrix G, you observe X, and you send it to the channel, then you can think of these sequence of bitwise channels. And look at a random matrix, they're going to be an increasing order, meaning that the quality of the channel improves through the sequence on average. And asymptotically, what's going to happen is the last information rate of the channel, fraction of them will converge to 1 and the rest will converge to 0. Meaning that the first, some fraction of them will be completely unreliable and the last bit of it will be completely reliable. So if you do the successive decoding, you're going to pick up some number of information bits in the end, and it's going to be exactly equal to the information rate of the underlying channel. And so this is it's because, again, this sequence of channels polarizes, meaning that it's either going to go to sort of the perfect channel or the complete erasure channel. So this idea can be put into a particular construction, and this was the original polar code construction, which I'll go through. Okay, so let's just look at the first step. So the idea is that you have a channel W that you're going to use for transmission, and you want to encode across it. So we think of using it twice. One's for bit x1 and another for bit x2. Now what we're going to do is we're going to send bit u1 and u2 through into x1 and x2 through this mapping. So essentially x1 is going to be u1 plus u2, and x2 will just equal u2. So what we get is a 2-input, 2-output channel from u1 to y1. And so we can think of it as a channel pairwise, as written here, but also, of course, it's just probability-wise, it just decomposes into the two parts. So we have u2 going over channel 2, and the sum of u1 and u2 going over channel 1. So we want to think of this as two binary memory symmetric channels by using the successive cancellation idea. So here, the generator matrix for this code is written here. Basically, x1 is just the linear combination of u1 and u2, and x2 is just equal to u2. So the idea is to use successive cancellation and think of the two copies of W as a sequence of two channels, W prime and W 2 prime. And from the transition probabilities, you can just write down what the two channels are. So the idea is that for the second channel, the idea is you're going to send U1 over its channel first and decode it. If you've decoded it correctly, then you can think of it as an observation available for U2. So we have these two channels, W prime and W2 prime, through successive cancellation. U1 goes to the two observations, and then U2 goes to the two observations and U1. And the probabilities are here. And the point is that these two channels exactly correspond to this W convolutions, check node and variable node, as in the earlier example. And so, so let's see why that happens. Okay, first of all, you can think of the bottom one first. It's a little bit easier. So if you want to transmit, so you're transmitting U1 over. Okay, so the way to think of this is like this. So if U2, okay, hang on, I lost my thought. Okay, so think of x1 and x2. So we know that u1, x1 plus x2 adds up to 0 modulo 2. So this is exactly the picture I have here on the right. So u1, x1, and x2 add up to 0 mod 2. x2 happens to equal to u2, but that doesn't really matter. So we're looking at channel from u1 to y1 and y2. So it's exactly this channel, right? And we saw before that this channel has density, which is essentially this check node convolution. So you can think of the decoding process by doing check node belief propagation, or equivalently, you can just think that this channel is a binary memberless symmetric channel, and it has density, which is given by this with respect to the original channel. Now, the other case, if I know U1, for example, if I know U1 is a 0, then x1 and x2 are equal, and it's just a repetition. If U1 is equal to 1 and x1 is the complement of x2, either way, because of the symmetry, the overall effect of the channel is the same, And the performance I'm going to see on the second channel from U2, Y1 and Y2 condition on knowing U1 is given by essentially a repetition code, which is this convolution of the two W's. Okay, so I can just repeat the process. So if I now take two copies of this structure, and then I have equivalent, so I'm thinking of doing successive decoding U1 followed by U2, U3 followed by U4, and now I just repeat. So I'm going to combine the first two channels and the second two channels in the same way. So now my input structure is going to look something like this, and I'm going to successfully decode in this order. So U1, then U3, then U2, and then U4. And the net channels are shown on the left. So essentially I'm going to start with the check node convolution and then do it again for U1. And for U3, it's going to be check node convolution followed by variable node convolution. And the other cases are shown here. And so what's going to happen then, if you repeat this process again, you get this same kind of structure. So now we'll have 8 input bits, 8 possible channels, and each one of them is going to be exactly some sequence of this check node, variable node convolution, 3 of them, and you get all 8 possibilities. So the net channels you're going to observe in this after doing successive cancellation is exactly equal to the full set of possibilities in the polarization process. Okay, so if we look at it from the the generator matrix perspective, so this is the original matrix, and then if we go to the next level, it has sort of self-similar structure. We're just substituting for each one a copy of the original matrix, and that happens again for the third level. So this is the generator matrix for the polar code, and this is the graphical representation. And just from looking at the number of nodes, you can see that the encoding complexity is roughly n log n. So the self-similarity structure in the construction allows you to do the encoding in sort of log n complexity, n log n. Now, turns out that the generator matrix of the polar code is closely related to a classical coding scheme called Reed-Muller codes. And the Reed-Muller codes correspond essentially to taking all the rows in the matrix of maximum weight. So this matrix is square, which means that essentially if you think of it as a code, it has rate 1. To get a lower rate, you take some subset of the rows. And a Reed-Muller code is constructed by taking a subset of rows that have highest weight. And the idea behind polar coding is to be a little bit more clever about the choice of the rows. So if we look at the channels that are generated by the successive cancellation, then what we saw before is this polarization effect, so that some of the channels, depending on the order, some of the channels are going to go to essentially perfect channel, and some are going to go to complete erasure. And what we want to do then is pick the rows that correspond to the good channels. And the ones which are going to be bad, we'll just declare known. So we won't actually we'll declare those bits known. So for example, if we want a rate 1/2 code, we would pick the best half of the rows, the best channels under the successive cancellation, take the best half and use that for the code, set the others to a known value, and then let that define the code. So the ones that are polarized to complete erasure, we essentially give the information to the decoder on the receiver side directly, and to the ones that have good quality, we use for transmission. Okay, so in order to illustrate the process, I'm going to show you. So this is a figure I borrowed from this website online. It's actually probably the best place to go if you want to get a feel for how polar coding works. And okay, so what you see here is a representation of the polar code. So on the left side we have the input bits, the input channels which have been ordered, and the different numbers represent the Bhattacharya parameter of the corresponding channel. So the red ones are the worst, in this case 9 out of 16, and the green ones are the best 7 out of the 16, meaning having the smallest Bhattacharya parameter, which represents the best channel. So the idea is that the bits corresponding to the red values are going to be declared known. So we're just going to set those bits to 0 and that will be known on the receiver side. Information will be loaded only into the green channels and then transmitted, and then they'll be encoded and transmitted over the channel. Okay, so this is just an example. So the red ones have all been set to 0. The green ones are given some set of values, the information bits. We encode through the generator matrix then to get the transmitted vector x. Each bit goes through Gaussian channel. Some observation is made, so in this case just some numbers. And then we go through the decoding process, and then in this case, okay, the decoding recovered the correct code word. And I'm going to look at the decoding process briefly. So let's look at the first bit. So the idea is, this picture may look a little bit different from the ones I showed you earlier. And all that's been done is, the input bits have been reordered to represent the correct successive cancellation ordering. So it's the same picture I showed you before, just rewired. So instead of having these long lines of parity checks, we do this kind of butterfly picture to get the ordering linear on the left. And so what I want to think about is decoding, say, the first bit, which is actually determined by the information. So the first, 7 channels are known. And now we want to decode this one. And so what's happening is that on the first set of bits are all known to be 0 with 100% reliability. Below this yellow line, all the input bits are completely erased. Now if you propagate that through the network, so when an erased bit goes into a check node, for example, or parity check, it essentially makes the parity check erased. So, I mean, any other information coming in is completely useless. If you have a known bit and it goes into a variable node, in other words, to a repetition, then that determines it exactly, and so it becomes determined. So what these yellow lines represent is the entire part of the graph which remains, which is sort of not determined. And you can see it has this sort of nested structure. In fact, what it looks like is essentially a computation tree, like an LDPC type computation tree turned on its side. And in a way, that's exactly what it is. So here are all the received values. And if you want to decode this bit, what you do is just propagate back through the tree. So the first, in this particular bit, has a structure which is, so in the polarization process corresponds to first doing the check node convolution followed by 3 variable node convolutions. So the decoding process then mimics that structure. So the first step, basically here, this represents a parity check relation. So these 2 values represent 2 bits on one side of a parity check. This is the third bit. And all you do is, if you just do belief propagation, you propagate that probability through. And that gives you, in this case, this is a likelihood, and that's the preferred bit. So here, from the values, you can see this is positive, this is negative, which means they're different, most likely, so that the parity check then was most likely to be a 1. And this represents the reliability, which is just a likelihood ratio. So 1 represents erasure, and anything smaller is more likely to be 1, anything larger is more likely to be a 0. So you can do the first step. You just go, so for each pair, you go through the operation, you do the parity check, and then you get these values. At the next level, we have this, at the next level we have a repetition. So actually, although this node looks like it's a parity check, the bit on the other side is completely known. So once you have a known bit going into a parity check, the other 2 bits have to be equal. So this is essentially just a repetition. So what it says is that these 2 values must be the same if this is a 0. If this is a 1, they would be opposite. In this case, we know it's a 0. So again, essentially what we have now is essentially just a repetition code. So the performance of the channel corresponds to the variable node operation, and it just propagates back. And we have another variable node and check. So when we want to decode that bit, essentially all we're going to do is decode this tree. And the information propagates through, and that gives you the decoded decision. Okay, the next 2 bits, I think, so the next 2 bits in the sequence were determined to be known. They were in the worst of the 9 channels. So the next one that we have to actually decode is this one. And you can see it has a similar structure. So at this point, we've decoded all the bits above, and we want to decode this one. All the ones below are erased, and what you end up with effectively is this kind of structure, which is very similar. And so the information propagates through according to the operations indicated at the bottom, and you decode that bit. Now the next one is very similar, and I guess the point of showing the two in a row is just to indicate that a lot of these calculations can be reused. So when you're doing the decoding, you can organize the calculation so that most of the computations at these nodes get reused. When you make a decision, you just propagate it back, and it corrects for the next stage. But essentially, the number of operations here is order n log n. So decoding complexity for this code structure is order n log n. And I won't show you the rest, but it's the same kind of picture. Okay, so here's in the bottom line of how we reach capacity. So suppose you have some target capacity C, and you have a channel with that information rate, so it can achieve that capacity C. Pick any rate less than C. Now go through this polarization process and pick a fraction R of the input channels to carry your information. The rest are going to be set to 0. Then as the code length increases, in other words, we do this polarization deeper and deeper, all of the bits that you've chosen are going to become these reliable channels. And the reliability goes to 0 on the order of like 2 to the minus n to the beta. Well, beta is roughly a half. So this is the rate at which the probability of error on those bits is going to go to 0. And if you even multiply by n, it's clearly also going to 0. So you can get the probability of error going to 0. So this means for some rate arbitrarily close to capacity using this scheme, you can achieve a low error rate. I should perhaps remark that the block sizes that are needed in order for this to happen are quite large. So even though it does go to capacity, this kind of construction is not really competitive against turbo codes or LDPC codes as it stands. Okay, so just a summary of the history of polar coding. So Erican announced polar codes in 2007 and showed that they could achieve capacity. Okay, the paper actually appeared in 2009. So it was 2009, Teletar and Erican showed the convergence rate is 2 to the minus the block length to the square root. So roughly this is the rate at which the error rate goes to 0. Density evolution interpretation was published by Mori and Tanaka in 2010, which I think simplifies enormously the understanding of the system. Okay, there are some improvements if you use larger matrices than these little 2x2 ones in the self-similar construction of the polarization. You can get better performance. You can get almost exponential performance. This was shown a couple of years ago by Karadas, Sasoglu, and Urbanki. Certain models of source coding, polarization is known to be optimal. And recently, Tal and Vardy have shown that you can improve the performance by doing some form of list decoding on top of the successive decoding. And this may make these systems competitive with the state of the art. It still remains to be seen. Okay. Okay, so that concludes the section on polarization. So now I want to sort of move to spatial coupling. So spatial coupling is the second approach that we know of, practical approach for achieving capacity. In some sense, it's a little stronger than polar codes because whereas the polar code that achieves capacity on a given channel can depend on the channel, turns out for spatial coupling this is not the case. So with spatial coupling, you can work this way. So you have a target capacity, you consider all channels which have capacity at least that number, and we can communicate at arbitrarily close to capacity with a good ensemble with a good code from an ensemble with high probability, which means we can pick essentially any member of this ensemble, and regardless of the channel, it should perform very well. And so this is an improvement, if you like, on polar codes in the sense that now we know we can pick one code and it's going to work well on any binary memberless symmetric channel. Okay, to try and give you a sense of how it works, I want to try another experiment. So So here we're going to start with a step function, a unit step function on the real line. And the idea is we're going to repeat two operations. So one is to convolve it with some smoothing kernel, which maybe we can just take to be a rectangular window. And after we convolve it, we're going to apply it some point-wise function h, and then repeat the process. Actually, to capture better the LDPC type structure, we're going to have two functions, which we'll call h sub f and h sub g. So we're going to alternate the point-wise iteration between h sub f and h sub g. Okay, so here is the first step. So on the left here, so the blue curve is just the unit step function. The function w is just this averaging kernel, so it has total weight 1. And the idea is then that the black curve is obtained by convolving the blue one with this function w. So it's just a smoothing operation. In this case, of course, we just get the ramp. Now we want to apply point-wise a function. In this case, we're going to use this one. So in the spirit of vector charts, I've written it sort of reflected. So the input is on the vertical axis and the output on the horizontal axis. So if we just apply this function now to that ramp, we get that red curve. So that's the update. And subsequent step is then just to smooth that again. So now we're just convolving again with this squared window function. So we smooth out the red curve, now we get the black curve. And now we're going to apply another function, which is this one here, which is written this way. So now the arguments on the vertical axis, and the arguments on the horizontal axis, and the outputs on the vertical axis. And so if we apply it pointwise to that black curve, we get this function here. And then we're going to repeat. So now, if we just repeat this, this is what happens. So this is an animation of a repetition of this process over and over. And you can see you get kind of these traveling waves. So these 2 points, this point in the middle actually corresponds with this fixed point here. Okay, I guess I'm going to repeat. So you can see, one thing you can notice is that there's certain spots, certain values where it tends to concentrate, and those actually correspond with the so-called stable fixed points of the effective density evolution, which is at the top right, this middle one, and the bottom. And maybe more simpler and more generic type version is this case here. So we have just the two curves like this, and in this case we get this left moving curve. And I've indicated these two areas, the yellow and the green, and you can see that the yellow is bigger than the green, and that actually corresponds to the leftward movement direction. Here's another example where now the green is bigger than the yellow, and now it moves to the right. Okay, here's another case where these two areas are actually equal. And I don't even know if you noticed, but actually it's still iterating, and we have a fixed point. So in this case, when the two areas match exactly, you get a fixed point structure. Okay, so that phenomenon I just showed you is the essence of spatial coupling, and these traveling waves are the key to achieving Shannon limit. And this fixed point structure with these balancing of the areas is the new phenomena that we observed that allows us to understand what's going on in the system. Okay, so you remember early on I talked about using density evolution to improve structural design for LDPC codes, and how we went through this evolution from regular codes, irregular, to these more complicated things. And I gave you a preview of spatial coupling. So in order to describe in more detail the idea behind the spatial coupling, I want to go to a different sort of representation of the LDPC type structures, the so-called protograph method. So here on the right, you see a very simple graph. I have two variable nodes and one check node. There's 3 edges each between each variable node and the check node. So this is altogether what's called a 3-6 structure. 3 edges per variable node, 6 per check node. And one way of thinking about LDPC codes is that you have some sort of canonical structure form like this represent the overall macroscopic structure. And the way you generate an actual code is you make many, many copies of these things and then do some random permutation on the edges. So the idea is that the structure on the left, which is some large graph with random positions for the edges, corresponds to this structure in the sense that the degrees of the nodes are exactly the same. So the sort of macroscopic connectivity structure is represented by this smaller protograph. But the way you want to think about it is that the protograph doesn't represent an actual small graph. It actually represents a very large structure. Okay. Now, I didn't go into it earlier, but I want to talk about, in LDPC codes, the LD stands for low density. And the idea of low density is that if you think about the parity check matrix, as the graph's getting bigger and bigger, the number of ones in the parity check matrix is only growing linearly in the size of the code instead of quadratically, which you have for, say, random codes. And if you think about the regular structures, like so for rate 1/2, you have 3, 6, 4, 8, 5, 10, meaning 3 ones per column, 6 per row, or 4 per column, 8 per row, and so on. As you go up and up in density, you're getting closer and closer to random codes, and not surprisingly, the code strength improves. So as you increase the degrees, we know that the code is getting sometimes better and better. However, if we look at the performance of belief propagation, it's getting worse and worse. And so among the rate 1/2 codes of this structure, 3, 6 turns out to give you the best performance and the highest threshold. And the reason is that the difference between the sort of local tree structure and the actual structure of the code is getting more and more pronounced as you move up this chain. So what's happening is there's two effects. So one is that the iterative performance, the sort of underlying tree structure, is getting worse and worse as you increase in the degree structure. But the actual code, which takes into account the repetitions in the tree, is getting better and better. And spatial coupling manages to bridge between these two regimes and allows you to convert essentially the threshold at the iterative decoding threshold towards the one given by the actual code. And this is the sense when we say that spatial coupling sort of saturates the threshold of the underlying structure, allows you to get to the optimal underlying performance of the code. Okay, so how does that work? So let's look at the spatial coupling construction. So the basic idea is now we take the protograph, so the representation of this LDPC code, and we make many copies. So you can think of this as a bunch of LDPC codes in parallel, all disjoint. So if each one of them has its own parity check matrix, then the net parity check matrix of the whole structure is just a diagonal structure. So each diagonal entry is just some big parity check matrix. And now what we do is we sort of spread the edges out. So in this case, what I've done is I've taken the protograph and taken one edge from each variable node to neighboring check node. So this is just sort of local spreading out of the edges. And if you look at the parity check matrix structure, it would just look like this. So basically, we've just spread out some of the edges. And I changed the color because now I'm thinking of spreading the edges out even further. However, now the yellow edges don't actually represent actual edges that necessarily are there. They're just probabilities. So the idea is that the edges are going to be spread out wider and wider, and there's some probability of going to a neighbor at some distance. In this case, I've spread it out by 5, but there's actually still only 3 edges. So what's happening to the parity check matrix is that the band is spreading out, but still has this overall diagonal structure. Okay, so this is the idea of spatial coupling. If you take this to the limit, you can have an infinitely long graph, and you're spreading out things locally more and more, and ending up with this diagonal structure. Maybe this is a good point to mention. So very early on, I told you that I didn't actually originally believe in the claims for low-density parity check convolutional codes. And the idea was that if you think about making this structure longer and longer, then its performance really can't be any better than the underlying LDPC code, which is, let's say, 3.6. What was happening in this protograph picture is that if you think about fixing the structure and letting each protograph get bigger and bigger, so that in the limit you're looking at sort of infinitely large code, not in the axis written here, but taking each node here and multiplying it infinitely many times, then in that limit it's no longer true that that dependence decays with distance. So it's no longer true that if I have some condition far away down the chain, that it will not affect what's happening locally. So in that, it turns out in this protograph type limit, it's no longer true that you have some local interaction. Okay, so to turn it into a block code, we just terminate. So at some point, we cut off the variable nodes, just declare them known, and trim them from the graph, and then what you're left with is a structure like this. So from the parity check matrix perspective, the end of the chain looks something like this. And what you can see, for example, is that the nodes corresponding to the first column have some parity checks of very low degree. So the first row has only one of these H matrices in it, so that corresponds to that check node on the very end that has low degree, which means those nodes are going to be getting a lot more information initially. So these check nodes have very low degree. That makes the information coming out of them more reliable. So what's happening is at the ends of this chain here, that these nodes somehow do better in the beginning. Okay, so I think I have an animation. Oh, before we do that. So here's a couple of parameters that describe the overall structure. So essentially we have this chain of length L, which is the number of copies we're going to lay out in the chain. And W represents the width of the spatial coupling. And just to, not to belabor the point, but in order to get to the Shannon limit, in order to get sort of threshold saturation, you want to let this W go to infinity and L go into infinity. So L going to infinity is necessary to make up for the fact that we're actually losing a little rate. So you'll notice that the number of check nodes is larger than the number of variable nodes, say, at the top. And so that means that we have more constraints, more than the number of variable nodes we have is less than twice the number of constraints, so the rate actually is slightly less than half. In order to amortize that out, you want to let the block length get larger and larger, and the endpoint doesn't matter. And in order to get the full effect of spatial coupling, you want to spread things out. Okay, so here's this is an animation actually of density evolution for that structure. And so what's going to happen? Okay, so I'm starting, these are the exit charts for the corresponding 3-6 structure. I'm making the channel gradually better as this moves down. And this is the fixed point of the density evolution. Or actually, I'm just running density evolution and you can see what happens. Okay. So I've stopped changing the channel. And you can see these waves propagating in. Okay. So let me just show that again. I think this might be the most important slide in the talk. Okay, so you can see initially what's happening is that in the middle we're essentially getting stuck, and that stuck point corresponds to this fixed point. But at some point something happens and you start to get these waves propagating in from the edges. And once that kicks in, they just propagate in, and eventually everything goes to zero, which corresponds to perfect decoding. So this is erasure probability. So at the end of the process, everything is decoded. So this is density evolution on the underlying sort of photograph description. So you think of this as representing the probability of observing an erasure on a particular edge is a function of this position in space. And what you can see is this effect of the boundary conditions propagating in. And in the limit is the number of nodes corresponding to each photograph goes to infinity. This will propagate indefinitely. Okay, so this phenomenon, this kind of wave propagation, is generic. I haven't really used any information theory in order to get here. So it applies to many, many other situations. So let me just mention a few. So one of the areas that's been applied is to compressed sensing. So in compressed sensing, as you know, I'm sure you're aware, the idea is that you have a sensing matrix, which is just some linear operator on some set of unknown vector, which you know to be sparse. So somehow the sparseness allows you to get away with an underdetermined system. You have some observations, and you know that the vector is sparse, and therefore, even though you have fewer observations than you have unknowns, you're able to determine the actual unknowns. And so the idea of using spatial coupling is to impose a sensing matrix like this. It looks very much like the parity check matrices I showed you. Essentially has this block diagonal structure. And at the termination, see in the top left, it's a slightly different to indicate you try to get things started up there. So up in the top left, you have more observations, and you're able to determine something about the first few variables in your unknown vector. And once those become determined, they essentially cancel out, and it propagates down the chain. So just recently, this is another picture representing spatial coupling for compressed sensing. Just recently in a paper, this paper here by Donahoe, Javin, Montanari, they were actually able to prove that this kind of structure can achieve the ultimate, it's called information theoretical limit for compressed sensing. So under sparseness assumption, what's called the L0 limit. So spatial coupling, the underlying phenomena, the underlying analysis that gives rise to this sort of wave type description is completely different. But you end up with a dynamical system which looks very much like the LDPC setting, and you get these propagating waves, and that's how you achieve the limit. That example is Gaussian Mach. So this is an example where universality really helps, because if you have a system with varying channels and you want to use a particular set of codes, let's say 2 users accessing the same base station with different fading, and you'd like to have a set of codes that will achieve the capacity region of that system. Spatial coupling codes can do that. And for that, this is where the universality is important, because you want a code that's going to perform well without knowing in advance what the fading is going to be. Okay, CDMA MAC, it's been demonstrated for if you attach spatial coupling on top of spreading sequences, CDMA, then by using the same phenomena, it turns out you can get significantly improved performance on CDMA systems. So the spatial coupling turns out to be a very powerful phenomena, has a wide range of applications, and I think people are just starting to get a sense of what it's possible to do with it. Okay, so let's now discuss how spatial coupling works in the LDPC case. Okay, so I want to go back now to the exit functions. So you remember when we were talking about density evolution, the simplest case is a binary erasure channel, and I showed you these 2 exit functions. So they represent density evolution as an input-output relation for the erasure channel. So essentially incoming messages has some erasure probability, outgoing message has some erasure probability, and that's just indicated by these functions. Right. This exit function, you can do it not just for the component codes, but actually for the entire LDPC code, or for any code for that matter. So imagine you have a big LDPC code, and you look at the erasure probability and all the bits in that code. So you have a bunch, pick one at random, and assume that the others go through some channel, and ask, okay, what's the entropy of the remaining bit conditioned on those bits having gone through the channel? Now, as a function of the entropy of the underlying channel, you're going to get some entropy of the outgoing bit. Well, in the erasure case, it just means what's the probability that the bit is erased. And if you do that in the LDPC setting, like the 3/6, asymptotically you get this curve. So, so if the channel is good enough, meaning the erasure probability is good enough, then the entropy of the outgoing bit will be 0, meaning that you're going to know the bit. So it'll be erased with probably 0. And then at some threshold point, you make a big leap up to that point where suddenly the bit is likely to be not determined, probably at 0.9, and as the channel gets worse and worse, that just degrades further. So this represents the true performance for an LDPC code in the limit on the binary erasure channel. So this is not the leaf propagation performance, this is the actual map performance or optimal performance. Now, one of the fundamental things which was discovered about these exit charts, at least for the erasure channel, was that they satisfy something called the area condition. So if you integrate this curve, then what you get is the code rate. So, okay, so this is formula for it, but essentially we're looking at the conditional entropy of the bit conditioned on the observations of all the other bits, looking at the average across the whole code, integrating across the input channel parameter and averaging by the number of bits. And what we get is just the code rate. So for example, for the ones I showed you, which I think I have a picture. Yeah, so for example, for the variable node, the area where we assume that one of the bits is going through the channel with known erasure probability 0.35, we integrate, we just get the effective rate of the underlying code, which in this case is 0.35 times a third. Okay, that's maybe a little complicated. So for the check node, it's very simple. You have, let's say, 6 edges coming in. If you have 5 of them and none of them are erased, it determines the 6th. If one of them is erased, it doesn't determine it. So this has, the code rate is rate 1/6, and if you integrate out the exit chart, the area is 1/6. For an LDPC code like this one determined by the photograph 3/6, if I integrate out that curve, I'll get the underlying rate of the code, which in this case is 0.5. Now for an ideal code, and when that's going to achieve the Shannon limit, this should look like this. So for rate 1/2, essentially if the channel is, say, worse than 0.5, the entropy is worse than 0.5, then basically the default code will fail. So this side, if the entropy is higher than 0.5, in other words, the channel is bad enough, essentially you get no information about the bit, and at some point you get a sharp transition to perfect decoding. So if the channel is good enough, you get perfect decoding, and then you get a sharp transition to complete erasure, and the area here has to be a half. So we know that the fact that the area is a half tells us that if you want an ideal code, that the transition has to be sharp, because the total area has to be 1/2, and if you want to make transition to perfect decoding at the limit, then it must be sharp, and we have no area to spare. So an ideal code has to look like that. Okay, so turned out there was a relatively complicated proof. Originally, it turns out that the area theorem for the binary erasure channel could be proved very easily, just in a couple of steps, using essentially the fundamental theorem of calculus and some information theoretic operations on the conditional entropy. Bottom line is that the area theorem is just a consequence of the fact that the exit chart value is essentially equal to the derivative of the conditional entropy of the underlying code as a function of the channel parameter. So this is something we can generalize. So if we look in general at what happens to the conditional entropy of the underlying code as we change the channel, we can define something which we call the generalized exit function for generalized channels. It's not quite the same as the exit function for the DEC. It doesn't have this simple form. Really what we want to do is look at one line above. So the simple form only turns out to be true for the binary erasure channel, but we can look at this functional. It turns out to be a linear functional on the densities, but it depends not just on the channel, but on the derivative of the channel as a function of its parameter. Okay. So another thing we can do then is just take the generalized exit function, look at it for under belief propagation. So if you imagine a code which is essentially this infinite tree picture that we saw earlier, and you think about the node in the middle, then we can look at its contribution to the generalized exit function, and it looks something like this. So let's see. Okay, so here on the left you see again the exit function. So the red curve is the check node and the blue node is the variable node. And what's happening is I'm changing the channel from ratio with probability 1 and improving it. And you can see what happens to the fixed point. Okay, maybe I'll show it again as it moves down. And on the right, what we're doing is we're taking from the fixed point, we know what the output performance is for the node in the middle, and we can trace out this sort of g-exit curve corresponding to that node in the middle. So for the binary erasure, it tracks this curve. Now at this point, we've reached the threshold of the iterative system. So if I decrease the channel anymore, the only fixed point that's going to remain is the one at 0, 0. And this point will make a jump down to here and go over into 0. In addition, though, there are some other fixed points. So if I go back up again, you see there are two fixed points. It's a fixed point where you typically get stuck, and there's another one on the other side. So I can track that curve, and if I do that, I get another branch of this curve. Now, it turns out that, so it turns out that if I look at this other this other branch, and I follow this entire thing, that this curved thing will actually carve out an area which is also equal to the code rate. Okay, so again, now we're not looking at the optimal g-exit curve for the underlying code, but only for this tree structure, and it has this funny shape, and because we're looking at the tree, we get this additional branch, but okay, it's on. At least it was on.
Do you think it's out of battery or?
I don't know. It's on. It's got a red light. Maybe the battery's weak, or not sure what it means.
No, battery. Yeah, it means battery is weak.
Oh, okay.
Do you want to change it now?
I can talk louder. I don't know. I'll try to talk louder. Maybe that will solve the problem.
Okay.
Okay. So. Okay. Okay, so in the general case, so it turns out this kind of picture holds for the general case, and that is that we can compute a curve even for, say, the Gaussian channel. So the top part of the curve corresponds to the fixed points you see from density evolution from forward decoding, and the bottom point corresponds to sort of unstable fixed points. But they can also be computed by looking at density evolution in one step and trying to modulate the channel value so that we pick up a fixed point, even corresponding to a particular target entropy. So, okay.
Sorry to cut you. Actually, it's very hard to hear you in the back, so let me try to.
Oh, sorry.
Can continue. I'll try to replace the battery. Those guys can't hear.
Okay. All right. So what I was describing was the calculation of this curve here, which is found by looking at all the fixed points of density evolution for the underlying code. And let's say this case looking at the AWGN. So here you have for each possible output entropy value, we try to find a fixed point that gives us an output density of that particular entropy. And then we can pick up this whole curve. And what we know that if this generates a smooth curve, then the area bound by that curve will satisfy the area theorem. The actual BP exit curve, which jumps down here, does not. So the interesting question is, what's the connection between this curve and the curve for the true code, the asymptotic code? Okay, so here I'm showing it for the binary erasure channel. And so the solid curve here is the one you generate from belief propagation, looking at all the fixed points. And the shaded region with this jump here is the one that corresponds to the asymptotic analysis of LDPC codes, of the actual optimal decoding. And so you might notice a few things. One is, for example, that the curves match at the top. So for the binary erasure channel, we know this is true. So the BP generalized exit curve and the actual exit curve match at the top for the binary erasure channel. They're exact. Okay, thanks. Oops, got the wrong part. All right. Okay, in the general case, we don't know this is quite true, though it's conjectured to be true. So what this means is that if you could optimally decode the LDPC code and you were essentially above this threshold, that the performance you would see between belief propagation and the optimal decoding are going to be the same. So the entropy you're going to see coming out of the decision is the same. Now, another feature is that these two areas match. So I told you that the area bound by this curve can also be shown to be equal to the rate. And we know that for the true exit function, the area under the integral is equal to the rate. So these two areas are equal, which means that these two carved out regions must also be equal. And this corresponds actually with the balance I showed you in the 1D exit chart picture, where the wave propagates to the left or to the right, depending on the imbalance, and only becomes fixed when the areas match. So asymptotically, we know that these two curves, these areas match. Okay, so what we can, in general, so what we define is what we call the area threshold. So given the BP curve, in general, we can look for the point where if we draw this shaded region, the area bound by it is equal to the rate of the code. And we define that point to be the so-called area threshold. Now, we believe that it's actually equal to the map threshold. So the optimal decoding threshold that we believe is this area threshold. That's known to be true for the erasure channel, not known to be true in general. So in general, we know that the entropy of the optimal decoding can only be smaller than the entropy under BP decoding. So it's actually, the BP curve is an upper bound for sure for the true curve, but we believe they're actually equal. Okay, so this is somewhat technical, so I don't want to go into the details, but it's a point that needs to be made. So essentially the point is that we know how to calculate the area. So each point on the curve, if you think back to the curve, so each point on this curve at the top corresponds to a fixed point of density evolution. And here the fixed point is just represented by x. So now if I pick any point along that curve, it's associated to some fixed point of density evolution x, and the area bounded by that shaded region actually has a closed form solution. And this expression here, the details aren't really important at this point. What's important is just understand that we have this particular expression for the area, and the actual integral of the g-exit curve has this form, and so the area threshold corresponds, as it turns out, to exactly this functional equals 0. So the point is we know explicitly in the LDPC case what this area threshold looks like in terms of the fixed point of density evolution at which it occurs. Okay, so what if, now we can try to do the same thing for a spatially coupled system. Try to compute the g-exit function. If we do that, we get something like this. So here's the area threshold for the underlying ensemble. So I'm looking at the 3,6. So the lightly shaded region is sort of the BP curve with the threshold corresponding to the BP threshold. The shaded region is the area threshold. Now, if we look at the curves we get from spatially coupled system with different lengths, this is what happens. So this is for length 4, 8, 16, and 32. So you can see what seems to be happening is the BP curve that we're getting for the spatially coupled system is converging to this area threshold of the underlying ensemble. Now, if you want to see what the actual fixed points look like, here's an animation. And you'll see it sort of resembles the decoding picture I showed you earlier. So the moving point is the point on the curve that's being computed, and the curves on the left represent the fixed point. So the bottom is the actual channel as a function of space, and the top is the internal messages. Now, in this case, it's a one-sided symmetry. I don't go into details, but for the two-side termination case, just think of this as just half of the picture. So I'll show it one more time. So you can see initially we're just following, initially it's flat, we're just tracking essentially the underlying fixed point of density evolution, and then you get this propagating wave effect, which is very much like the decoding. So each of these points, it's not actually moving, understand that each of these points is a fixed point of the underlying density evolution. What we're changing, we're just showing the set of all such fixed points. Okay, so without belaboring the point, I think what we claim is what we know how to show now is that phenomenon actually occurs. So in other words, the spatially coupled system asymptotically, its threshold will approach the area threshold of the underlying system. And we also know how to show that if we increase the degrees larger and larger, that the area threshold will converge to the Shannon limit. So if you look at a very large, relatively large degree underlying ensemble, you can see that the leftmost point of the curve is moving to the left, which tells you that the leaf propagation performance is getting worse and worse, but the curve is getting flatter and flatter on the top. And so what's happening is the area threshold is converging to the Shannon limit. So if we have an underlying system that can achieve that threshold, we'll be able to reach the Shannon limit. That's the idea. Okay, so just then to understand what's going on from the belief propagation perspective, and density evolution perspective. So one way to think about density evolution is just this update between what happens at the variable nodes and what happens at the check nodes. So essentially you have some update function, and the update is on the representation of the underlying channel. So the quantities being updated in general are probabilities representing binary memory symmetric channels. So we have an update at the variable node side, we have an update at the check node side. So what happens when we go to spatial coupling, at least if we think of the infinite case, so the unterminated case, it's the same picture, but instead of just having sort of point-wise evaluation, we imagine the same quantity distributed across the real line. So we have, across the real line, we have, for each point in the real line, we have a value of a density. And the operations consist of the same operations with the addition of the spatial averaging. So we do some kind of spatial smoothing before we go to the other side, and then we do the update locally, and then do spatial smoothing on that side and go back. So it's exactly the same set of operations, except for the addition of this smoothing in space. Okay, so the density evolution of the two things corresponds, and that's what connects the fixed points of the underlying ensemble to the spatial couple case. Okay, so if you remember the exit charts for the binary erasure channel, and I showed you earlier this preview where I said that when these areas between the two curves, when they're balanced, that's going to be a new threshold. And that new threshold corresponds exactly to the fixed points of these waves that occur in the spatially coupled system. So in the spatially coupled system, what matters is exactly the shaded region, so the region below the BP fixed point. This is where all the action is, if you like, in the spatially coupled part of the system. Okay, so I showed you earlier that if the areas are balanced, then these 1D systems give rise to these fixed points. So this is something we can prove, and in fact the proof is relatively easy that it's a necessary condition. So I'll just quickly, I can show it to you. So the updates look like the equations on the top. So you have these functions f and g, which we can think of as just functions on the real line, and the operations are convolution with a smoothing kernel followed by point-wise functional updates. Now there's another way to write these equations down using the inverse. So if you imagine that f and g are monotonic, meaning they're, say, in the limit of minus infinity they're going to 0 and plus infinity going to 1, so they're monotonically increasing, then we can write down this iteration in terms of the inverse functions. And if we do that, we get this form. I don't want to go through, of course, the actual derivation of it. The point is just to note the symmetry. So we have this function omega, which is just the integration of the smoothing kernel, which itself has certain symmetry properties. And inside we get two terms, one depending on each function, f and g, and essentially integrating out one side or the other. And on the left-hand side we have the update function. So this is just another way of writing down the equations on the top using the inverse functions. But because of the symmetry, it's clear that if you integrate these two things and you're at a fixed point, meaning the f's and the g's no longer depend on t, and just by integrating out, you can easily conclude then that the integrals, the sum of the integrals of these two functions, and their inverse functions in particular, have to be 1. So just from the form here, you can see that the arguments inside the integrals are the same except for the sign of the argument. So just from that form, it follows that you have this condition that the area of the integrals have to sum to 1 if there's going to be a fixed point. Okay, so what that means here in this binary erasure setting is that this is the area up to the fixed point of the check node exit function. This is the area of the variable node exit function. Those two things have to add up to 1, which means equivalently that these two areas have to be the same. So the yellow and the green areas have to be the same, and that's necessary in order to have this spatial fixed point. So the point, the underlying phenomena is that with spatial coupling, you get this new set of fixed points, which are these sort of monotonic fixed points that interpolate between the two extreme fixed points, the one on the top right and the one on the bottom left. In order for it to be a fixed point structure, this balance condition has to hold exactly. So unlike the other fixed points which move around as you change the channel parameter, these ones only exist exactly at this point. And what happens if you move away from it is they start to get these traveling waves. So it becomes a fixed point only in this exact condition. And this exact condition turns out to be exactly the area threshold. And that fact is what makes it provable that this system will achieve the exit curve will achieve exactly this area threshold phenomenon because of the existence of these fixed points. Okay, so let me just wrap up how the general argument goes. So this area condition in the general case also has an interpretation. Obviously, I don't have a simple graphical picture to show you, but the basic idea is the following. So the integral of those two curves corresponds to some integral across space of the fixed points. And the limits at the two ends of the fixed points correspond to the fixed points of the underlying system. So maybe going back to this picture, so the fixed point corresponding to this system has one limit with a fixed point there and the other limit with the fixed point there. And that property holds in general. So if the underlying system in some more general channel case, you get a fixed point like this, it has two limiting distributions, one that's say plus infinity, one at minus infinity, and the integral condition, the fact the areas have to balance, boils down to this area condition, these A functional being equal. So if you remember, the A functional corresponds to this term representing the area of the G exit functional. So what it says is essentially this, that the area condition can be expressed in general for arbitrary densities and has a particular form like this. And if we, in particular, we know the left limit is a perfect decoding, so the area there is 0, then this A functional has to be 0 on the other end. And what that means is that, okay, so we know that these two things have to match, and if we force, let's say, the left limit to have this A functional 0, which corresponds to perfect decoding, we get the same on the right. So what that means is that the x infinity is the BP fixed point at this channel parameter that has to be at the channel parameter where the area threshold is satisfied. Okay, so let me just try and reiterate that to make it a little more clear. So this area condition, the fact that these two areas balance is exactly equivalent to the condition in the G exit picture here. Well, say here. So the fact that these two areas balance is exactly the same statement, it turns out. So that still works in the general case. And what I'm saying is then that the area condition in the general case tells you that in order to have a fixed point across the spatial system, the channel parameter has to be such that exactly at this area threshold, okay, this balance condition holds. Okay, so finally, in order to get then to the Shannon limit, we say that in the terminated system, once we're beyond the termination point, we're essentially forcing the system into perfect decoding. So at some point outside of the finite range of the system, outside of the region actually supported by the code, we've effectively removed all the variable nodes. So in equivalently, we've decoded them perfectly. So on the boundaries, we essentially force a solution to perfect decoding. So if the system's going to get stuck, it has to get stuck in some kind of fixed point that has one limit equal to perfect decoding. And we know then now that such a fixed point cannot exist unless we're at least at the area threshold or worse. Which means once we're below the area threshold, the system will not support any other fixed point. So that's how you get to the Shannon. So the system has to converge once the channel passes that area threshold point. Okay, so that's a final animation just to show how we connect, so the existence of this fixed point in space to the existence of the fixed points that generate the exit chart. So this picture just shows how they're connected. This is for the doubly terminated case. So if you imagine that this is a fixed point in space, and what we do is we just take a window and slide it across, and from it we construct approximately a set of fixed points for the underlying finite spatially coupled system. So that thing hopefully reminds you of the G exit picture I showed you earlier. So this The fixed point space corresponds to a bunch of fixed points for the underlying ensemble, and those are the ones corresponding to the vertical part of the G-exit picture. Okay, so turns out that there's a close analogy between all these systems and a lot of stuff in statistical physics. There's a phenomena in physics that corresponds to this, and it's actually nucleation. And so this something. So let me just show the video, illustrate the point. Okay. Well, we don't have the audio, but so what happens is this is supercooled water. So this is water which is actually below the freezing point, but for some reason it's not freezing, it's stuck in a liquid state. But if you initialize it at the boundary, in other words, give it a little ice crystal, then the whole thing nucleates. And this process actually corresponds to the propagation of the wave in the spatially coupled system. And that's the phenomenon I missed, and that's why these codes can achieve capacity. Okay, so that's it. Thank you.
So, question.
Quick question. Are these related to spinal cords at all? Or?
No.
There are some kind of nonlinear convolution cords.
Yeah, I know what spinal codes are, but no, this is a different phenomenon completely. So I don't want to go into what spinal codes are, but yeah.
Any more questions?
I wonder whether the polar code has been used in practical variance communications.
Not to my knowledge, not yet. And I think that from a performance standpoint, generic polar codes don't perform as well as LDPC or turbo codes yet. There's some work, Alex Vardy's work, in particular using list decoding. He claims that they do become competitive. However, as I said early on, we're already so close to capacity, it's really hard to introduce a new coding system into any current technology. You need some significant advantage in complexity if you want to sort of change the paradigm. And so far, that hasn't been demonstrated in a compelling enough way.
Yeah. Okay, Dr. Richardson is going to be around parts of the afternoon, so feel free if you have any questions, anything you want to ask, walk in with your questions. Let's thank him again for the wonderful lecture. So, a couple of announcements actually. The first one is about the meal cards. They have insisted that for some reason they want you to return it back at the end of the... oh, you can't hear it. Maybe can I use that?
I don't think it's working.
Is it working?
It's ready. So.
Okay, it's no. So the first thing is about the meal cards.